Hi everyone and welcome back. In this lecture we will create the custom dataset for our cardiac detection task. It has to load and return an X-ray image together with the coordinates of the bounding box around the heart. As usual, let's start with the imports. We will use pathlib for easy path handling, PyTorch for dataset creation, NumPy to load the pre-processed images, Pandas to read the CSV file containing the labels, EMGAug to set a seed for the random augmentations. We will discuss later why this is necessary. And last but not least, the bounding box class from EMGAug to automatically augment image and bounding box in the same way. Alright, let us define the dataset. As you already know, we need to define the len function, which returns the length of the dataset, and a getItem function, which returns the image and corresponding bounding box coordinates. Let's get started by creating the class. We call it cardiac dataset, which inherits from torch.utils.data.dataset. At first we define the constructor. It accepts besides self the following arguments. At first the path to our labels CSV file. Next, the corresponding patient ID NumPy files, therefore either our train or our validation patients. Of course, the root path to our pre-processed train images. And last but not least, our EMGAug augmentation pipeline. First off, we read our labels CSV file and store it in a variable called self.labels. Second, we use numpy.load to read the subjects provided by the patient's argument and store them in a variable called self.patients. After that, we create a variable called self.root path, to which we assign the past root path converted to a path object. This allows to either pass a path object or a plain string. Last but not least, we assign our augmentation pipeline to self.augment. Now we can define the len function, which returns the length of the dataset. We define __len__, which only accepts the self argument, and then returns the length of our self.patients list. It is either 400 for the train dataset or 69 for our validation dataset. Alright, we are ready to implement the actual logic in the __get item ___ function. It of course accepts the self argument and an index, let's call it IDX, describing which subject should be loaded. Above all, we have to access the subject in our self.patients list at position IDX. Let's define a variable called patient, to which we assign the element at position IDX of self.patients. Next, we need to grab the entry from our labels data frame that matches the patient we just extracted. Let's write data equals to self.labels, where the name column of self.labels is identical to our patient ID. Since we have ensured when creating the dataset that each patient occurs only once, this statement will retrieve the exact entry from our labels data frame that corresponds to the above patient. Now we can extract and save the bounding box coordinates for that particular subject. Let's start with x0. Therefore, we could write x_min equals to data of x0 dot item. We call .item as pandas otherwise would return not only the value we are interested in, but also additional information such as index or type. We perform the same operation for y0. To store the coordinates of the lower right corner, we should at first remember that our labels data frame includes width and height instead of the actual coordinates. Therefore, we have to calculate the individual values by both adding the width to xmin and the height to xmax. Let's store both coordinates in the variables xmax and ymax respectively. Last but not least, we only have to concatenate those 4 coordinates into our bounding box list. Let's write bbox equals to the list containing x underscore min, y underscore min, x underscore max, and y underscore max. Alright, now we are ready to load the corresponding X-ray image. At first, we need to define the file path to the image by concatenating our self.rootPath variable with the name of the patient. Next, we can load this image by using numpy.load, to which we pass an f-string containing the file path as a variable and the file extension .npy as a normal string. F-strings are another way to simply add a file extension. Don't forget to change the d-type to float32. Cool, we successfully loaded image and bounding box. Now we have to tackle the most important step, the application of data augmentation to image and bounding box. At first we check whether an augmentation pipeline exists. If that's not the case, we are in the validation dataset and don't want to apply augmentation. Second, we create a bounding box object by using the bounding box class from emg.org, where we simply pass the individual values to the coordinates. At first x1, which gets the first element of our bounding box list. Next y1, to which we assign the second element of our bounding box list, followed by x2, which gets the third, and last but not least y2, which accepts the fourth. Before moving on, we need to fix a crucial problem. Due to multi-threading in combination with the PyTorch data loaders, all augmentations are continuously repeated and not randomly applied when using emg.org. With this, we would lose the whole advantage of data augmentation. Please take a look at the corresponding Jupyter notebook of this lecture, as it contains 2 links that also demonstrate the problem. Fortunately, the fix is quite simple. We use PyTorch to create a random integer and assign this integer as a seed to the emg.org environment. In code it looks as follows. We create a variable called random_seed, to which we assign a random integer via torch.rand int in the range between 0 and 100,000. Additionally, we need to pass a tuple defining the shape the returned integers should have. In our case, it's simply one value. Subsequently, we call .item to convert this tensor into the single random scalar we want. It is really important to use PyTorch to create the random numbers and not NumPy or some other library, because at this moment only PyTorch can handle the combination of data loaders and multi-threading. After that, we use emg.org.seed, to which we pass our just created random seed or random integer to finally set the seed. We are now ready to augment the X-ray and corresponding bounding box. To do so, we use our augmentation pipeline self.augment. It accepts an image and bounding box argument, augments them identically, and returns the augmented X-ray and bounding box. Thus, let us write emg.org_bbox equals to self.augment, where we use our X-ray image as image and the bounding box object as bounding boxes. Last but not least, we have to extract the augmented bounding box coordinates from the returned 2D array to bring them back to our desired shape. Let's write bbox equals to arg underscore bbox 0, 0. This corresponds to the x coordinate of the top left corner. Arg underscore bbox 0, 1, which corresponds to the y coordinate of the top left corner. Arg underscore bbox 1, 0, which is the x coordinate of the bottom right corner. And last but not least, arg bbox 1, 1, which corresponds to the y coordinate of the bottom right corner. Awesome! We just finalized our augmentation. The last step we have to perform is to set normalize the image by subtracting the pre-computed mean followed by division by the standard deviation and convert both image and bounding box to a tensor. Additionally, we directly add the channel dimension to the image by using unsqueeze. Alright, at first we can write image equals to image minus 0.494, which is the mean we computed in the previous lecture, divided by 0.252, which is the standard deviation. Next, we convert the image to a tensor by writing emg equals to torch.tensor, to which we pass our image, followed by calling the unsqueeze function. Last but not least, we convert our bounding box coordinates to a tensor before returning both image and bounding box. Perfect! Our dataset class is complete. In the next short lecture, we are going to evaluate it. Thanks!